In this video, I'm going to solve some example synchronous machine problems. So to start out, let's assume we have a 480 volt, 50 hertz, Y connected, 6-pole generator. And we have a synchronous reaction of 1 ohm per phase. Synchronous reactance. And let's assume that we have an armature current at full load of 60 amps. And that is going to be at 0.8 power factor lagging. We have some losses. We have a 1.5 kilowatt loss for friction and windage. And we have core losses of 1 kilowatt at 60 hertz at full load. Now in this problem, we're ignoring the armature resistance, so no I squared R losses here. And we assume now that the field current is adjusted so that the terminal voltage is 480 volts at no load. Okay, and we want to figure out a few things here. We want to figure out the speed of rotation. We want the terminal voltage, of the generator if we do the following things. One, if it is at rated current at 0.8 lagging. And then secondly, if it is rated, if it's loaded at rated current with a power factor of 1. And then third, if it's loaded with rated current with a 0.8 leading power factor. We want to know the efficiency of the generator when it's operating at the lagging, at the 0.8 lagging. And that's at rated current. And we want to know how much shaft torque must be applied by the prime mover at full load. Finally, we want to know the voltage regulation at the 3 different power factors that we discussed. Okay, so first let's figure out some general things that are going to help us with the problem. So we know the generator is Y connected. So since it is Y connected, the phase voltage V phi is going to be equal to the terminal voltage divided by the square root of 3. So when the terminal voltage is equal to 480 volts, as it is here, the field current was adjusted, right, so that Vt at no load was 480 volts. Let's just put no load here. The phase voltage is going to be 277 volts at no load. And of course, at no load, the armature current is 0. A no load equals 0. So the armature reaction voltage drops to 0. And then the internally generated voltage EA is equal to V phi, right? So whenever IA is equal to 0, EA is equal to V phi. So this is all at the no load condition. Now the internally generated voltage EA, remember EA is equal to K phi omega. So this is only going to change when the field current changes. And in this problem, field current is adjusted initially so that we have 480. So that we have 480 on the terminal at no load, and then we're not going to touch the field current for the rest of this problem. So the magnitude of EA is 277 and will not change in the problem. Okay, so let's look at part A. In part A, we're asked to find the speed of rotation of the generator, and the relevant equation here is Fe equals Nm over 120. So Fe here is the electrical frequency, Nm is the speed that we're looking for, and P is the number of poles. We can solve this equation for Nm. So Nm is equal to 120 Fe over P, and of course we have all of these values given in the problem. So we have 120. The electrical frequency we were given as 50 hertz, and we were also told that it's a 6-pole machine. So the speed here is 1,000 RPM. If we wanted to convert this to radians per second, we would get 104.7 radians per second. Okay, part B asks us to solve for the terminal voltage of the generator under 3 different conditions, right? So this is where we had the 0.8 lagging, the power factor of 1, and 0.8 leading. So we're looking to solve for terminal voltage under these 3 different conditions. So in the first one we're going to look at is if the generator is loaded at rated current with 0.8 lagging power factor. And so we can think about the phasor diagram that we would get under these conditions. We're going to take V phi, the phase voltage, at an angle of 0. So that phasor is V phi. And then we've got, we have a lagging power factor here. So if we just sort of project here, IA, if this is our IA, and then let me just draw this dotted line out here so that I get a right angle going through here, then this line would be my JXSIA phasor. And then here's EA. And then, of course, if I just want to drop that here, this value is XSIA sine theta, and this value is XSIA cosine theta. And here where this angle is theta. And theta is equal to 36.87 degrees. Okay, so that's our phasor diagram. Now, in the diagram, again, we know V phi is at an angle of 0, and we know the magnitude of IA from before. It's 277, or EA, I'm sorry, I think I said IA there. The magnitude of EA is equal to 277. And so the things that we don't know are the angle, this angle delta, which is the angle between V phi and EA, and we don't know the magnitude of V phi. So we need delta, and we need the magnitude of V phi. Okay, but from the figure, and the right triangle that we have here, we can write the following equation. EA squared is equal to V phi plus XS IA sine theta squared plus XSIA cosine theta squared. So all I'm doing is I'm taking this right triangle and we're doing A squared plus B squared equals C squared. Okay. So I can just start to fill the values in this equation. On the left-hand side here, we have 277 volts squared. And this is equal to V phi, which we don't know, plus, well, XS we're given to be 1 ohm, IA 60 amps, given in the problem, sine 36.87 from our phasor diagram, this quantity squared, plus, again, 1 ohm times 60 amps times cosine 36.87, that quantity squared. Okay, so now I just need to solve this for V phi, and I get 76,729 on the left-hand side equal to V phi plus 36 squared plus 2304 And if I just reduce this and solve it for V phi, I get V phi is equal to 236.8 volts. And now we know the generator is Y connected, so Vt, the terminal voltage, which is what we were asked for, is equal to root 3 V phi. So the terminal voltage when the generator is loaded under this condition would be 410 volts. Let's look at the same idea when we are at unity power factor. So at unity power factor, we can draw the phasor diagram. We have V phi. This is JXSIA, because IA is going to be in the same direction as V phi. Here's EA. That's our angle delta. And we can proceed from there. This situation, it's a little bit simpler. We have EA squared equal to V phi squared plus X sub S IA squared, because it's already a right triangle. So this is going to be 277 squared equals V phi squared plus 1 times 60, that quantity squared. We get again 76,729 is equal to V phi squared plus 60 squared, or 3,600. Let's just do 3,600. And so V phi squared, we just solve this for V phi squared, equal to 73,129. V phi then is equal to 270.4 volts. And from there, we get the terminal voltage equal to root 3 V phi, which is equal to 468.4 volts. Finally, when the generator is at 0.8 power factor leading, we have our phasor diagram. Once again, V phi at an angle of 0. And now IA is going to be somewhere off in this direction. And so JXSIA is going to look something like that. And of course, we have EA here, which is still equal to 277 volts. If I drop this guy down here, this is XSIA cosine theta. And this here is XSIA sine theta. Okay, so we're going to do a very similar thing. To find V phi here, we have EA squared is equal to VP minus XSIA, that quantity squared, plus XSIA cosine theta quantity squared. Again, theta is that angle, where this again is IA, the angle between IA and VP. And so what we're doing here is this value, XSIA, actually it looks like we should have sine theta here. XSIA cosine theta quantity squared. Okay, so this distance here, from here to here, if we subtract that from VP, we're left with this. And so that is one leg of this right triangle that includes EA, and then we're just doing A squared plus B squared equals C squared for that right triangle. So same idea as before, except we need to subtract. Okay, so we plug our values in here. 277 squared equal to VP minus 60 times sine 36.87. That whole thing squared plus 60 cosine 36.87 quantity squared. And we get 76,729 equal to VP minus 36, that quantity squared, plus 2304. So we can subtract on the left-hand side. We get 74,425 equal to VP minus 36 quantity squared, and then take the square root of both sides, and we get 272.8 equal to VP minus 36, and finally we get VP equal to 308.8. And so again, we're y connected, so VT is equal to root 3 VP, which would equal 535 volts. Okay, in part C, we are asked to find the output power of the generator at 60 amps and 0.8 power factor lagging. So P out is equal to 3 VP IA cosine theta. Again, 3 because our model is per phase. There's 3 phases. So 3 VP IA cosine theta. And we have these values. 3, right? We have VP from the previous part of the problem. VP in this case was 236.8. We know IA under the rated condition is 60 amps, and then of course cosine theta is 0.8. That's our power factor angle. And this gives us 34.1 kilowatts. Okay, so 34.1 kilowatts, our input power, P in, is equal to our output power plus our losses. So our I squared R losses plus our core losses plus our mechanical losses, or our friction and windage losses. Okay, so we have all of these values. P out, we just solved 34.1 kW. We assumed that there were no electrical losses in this problem, so that's 0. Our core losses were given in the problem to be 1 kilowatt, and our mechanical losses were given to be 1.5 kilowatts. So therefore, if we add all that up, it tells us what our input power was. And our input power then was 36.6 kW. And so now we have the output power, we have the input power, we can find the efficiency. So it's equal to P out over P in times 100%. And so this is going to be 34.1 kW over 36.6 kW times 100%, and we are operating at 93.2% efficiency. Okay, and that's part C. In part D, we are asked for the shaft torque applied by the prime mover at full load. Okay, so we can start out, we know the input power now, so we can use the equation Pn is equal to the applied torque times the speed, and we'll solve this for the applied torque. The applied torque is equal to Pn over omega m. And back when we found the speed, we converted it to radians per second. So here we are at Pn from the previous part of the problem, 36.6 kW, and speed 125.7 radians per second. So it's important to remember that when you're using this equation for torque, you need speed in radians per second. At any rate, this is equal to 291.2 Newton meters. Okay, and now part E asks us to find the voltage regulation of the generator when we are at 0.8 power factor lagging, at power factor of 1, and at 0.8 power factor leading. So those three conditions that we've been dealing with in the problem. So voltage regulation is equal to the no load voltage minus the full load voltage divided by the full load voltage times 100%. We've got three cases. First, let's look at the lagging case. 0.8 lagging. In this case, we had a no-load voltage. Well, in every case, we have a no-load voltage of 480. Because in every case, when there's no load, IA is equal to 0. And we're told that the field current is set up for a terminal voltage of 480. That's how we got that's how we deduced that EA was 277. So we have 480 volts minus the full load voltage, which in the lagging case we computed that to be 410 volts, and we divide this by 410 volts times 100%, and we get 17.1% voltage regulation. If we do the same thing in the unity power factor case, again we have 480 480 volts. And in this case, the terminal voltage when we were at unity power factor and rated current was 468 volts. And so if we crank through that, we get a voltage regulation of 2.6%. And then finally, in the leading case, our voltage was calculated to be 535 volts. And this comes out to be minus 10.3% voltage regulation.